All right, we're going to continue RTDSP Project 4 demonstration. So in the last video, I talked about designing the notch filter using the transfer function. So now we're going to talk about cascading a cascaded bandpass filter using RC low-pass filters and high-pass filters in cascade with each other. And we're going to cascade 4 low-pass filters and 4 high-pass filters together. So to start with, we're going to talk about a little bit of theory regarding RC filters. So the basic RC filter is just a first order, since there's only one capacitive element. It's a first order filter. So the low pass filter just looks like this, where it has the resistor and the capacitor. And so we can derive the transfer function from through circuit analysis because we can say that the derivative is the same as S. So I do this first in the time domain, and then I convert into the S domain by taking all the derivatives and writing them as S. And then I rearrange to solve the transfer function in terms of S. And so after performing some math around here, we see that we have this, and this 1 over RC can actually be replaced with the omega cutoff frequency, or the angular cutoff frequency, because if you remember, 1 over 2 pi RC is the cutoff frequency. So that means right here, the cutoff frequency is 1 over 2 pi omega. So we can rewrite this as the angular frequency is 1 over RC. So this can help simplify our equation. So what this is really saying is that I don't actually need to specifically design a resistance and a capacitance in mind. Since I'm designing a filter, I'm instead just going to design based on what I want my cutoff frequency to be, and not worry about the specific values of resistance and capacitance in my design. So the high pass filter is almost the same thing, except that the orientation of elements has been changed. So now the capacitor is in series and across the resistor. It's the same process though. We start off in the time domain and we have to use derivatives, and we convert these derivatives into S. And then from there, we just need to rearrange the equation to solve for ys over xs, which can be written as the transfer function in terms of s. And so this is what we get for the high-pass filter. And again, like last time, we see that we can rewrite the cutoff frequency and the angular cutoff frequency by substituting R and C. So in this way, again, we don't have to use specific values of resistance and capacitance. Instead, we can design based on what we want our cutoff frequency to be. So this is the high-pass filter transfer function. It looks similar to the low pass cutoff, or the low pass transfer function, except there's an S instead of an omega in the numerator. So with these two transfer functions in mind, they're a lot simpler than the notch filter. So we're going to do the same thing. We're going to generate the IIR filters for these using the impulse invariance method and through bilinear transform. So the first thing we're going to do is impulse invariance. So we're going to start with the low pass filter. So this is what the transfer function looks like in the S domain. So we can use the inverse Laplace transform to rewrite it in the T domain. And then we can sample in the T domain to get to the discrete time domain, N domain, by taking T equals NTS. And then I'm going to make this substitution to make this into a form that's easy to transform into the Z domain. And so then now we have the Z domain right here. Now the high pass filter, in general, you don't want to use impulse invariance for the high pass filter. But just for the sake of theory, I went ahead and tried deriving the impulse invariance of a high pass filter. I don't use this equation though, because when I use this equation, and the scaling doesn't come out right and the function doesn't look quite right. So instead I use the bilinear high pass filter for both cases, since I can't use the impulse invariance for a high pass filter. So again, this is what we started with. We can remember S is the same as the derivative, and then I can just rewrite this using the reverse Laplace transform. That'll take the derivative, and remember for the derivative of u of t is where we get this delta function. And so then we sample to change from the T domain to the discrete time domain, the N domain. I make a substitution here to write it into a form that's easy to transform into the Z domain. And then we have it in the Z domain. And then from here, we just rewrite this in terms of Z. And this, we can easily derive our transfer function from these Z domain equations. So Now for the bilinear transform. So the bilinear transform, we just make the same substitution, s equals 2 over t, and with this quantity, and then you just have to usually multiply by this denominator to rearrange it, and then rearrange it to appear in proper form. In this z transfer function, we can easily create the difference equation from, because each of these z to the -1 or -2 is going to be a delay. And the high-pass filter is the same way. You do the same substitution and you rewrite it, and it comes out looking like this. So, oh yeah, it looks like this, but we rearrange it looking more easier to see, form that's easier to see the different coefficients for our difference equation. So for cascading filters, when you cascade filters, you would do the convolution of the filters in the time domain, which is the same as doing multiplication in the frequency domain, S domain, or Z domain. So in this way, we can cascade two filters by just multiplying the two filters together. So since we're going to be doing fourth order low pass and fourth order high pass, that means I need 4 low pass filters and I need to multiply them all together, and I need 4 high pass filters and I need to multiply the transfer functions together, and then I'll need to combine those low pass and high pass filters together. I'm multiplying those cascaded filters by each other. So that's a lot of multiplication, and you can write it out, but instead of trying to write out all the multiplication, I think you use like Pascal's triangle to help you generate some of those coefficients. But instead of doing that, we can just use the MATLAB convolution command. So the MATLAB convolution command can be used for vector or for polynomial multiplication by just using inputting the coefficient vectors for the polynomial. So in this way, I only have to generate the coefficients for the first order, and then I just do repeated convolutions to multiply them by themselves to get the higher order filters. So with that in mind, it's not 5. I originally thought it was 5, but I only need to cascade 4 filters on top of each other. So as you can see here, I just take the first order low pass filter and then multiply it by itself 4 times using the convolution. And I did the same thing with the high pass filter. I multiply it by itself using the convolution. Then I need to multiply these 2 quantities together using the convolution. So by using the convolution command in MATLAB, I don't actually have to write out all the multiplication because MATLAB will take care of it for me. So with that in mind, let's talk about MATLAB real quick. All right, so here in MATLAB, we have the low cutoff frequency, and this is kind of backwards because the low pass filter will actually determine the maximum or the high point of your frequency in your band pass filter, and the high pass filter determines the lower cutoff frequency of the band pass filter. So this is going to be a band pass filter from 1500 to 3000 hertz. And I generate the impulse low pass. I generate the impulse high pass, but like I said earlier, I don't actually use this impulse high pass because when I tried implementing this, it didn't work, and that's because the impulse invariance method does not work well with high pass filters. And then I have the bilinear low pass filter and the bilinear high pass filter, and then I need to cascade the low pass and the high pass together, and then I output them as coefficients to be written in C. So we're going to start, I believe, near the bottom, since I did this. Okay, impulse high pass. Let's start with where is it? Impulse low pass filter. So this is going to be the same. So this is the alpha that I derived in here. So let's go back to impulse low pass. This is what this alpha here is, e to the negative TS omega C. This is that alpha here. And this is just the coefficients of the numerator. So this is the numerator, which is in the coefficients of it. So this is the scaling factor, and then this is the denominator. So this is going to be the, let me just put this over here so we can talk about this real quick. Right, so this is going to be the 1 minus alpha is this part right down here, and this top part is the omega C divided by f of s right there. And so then I perform some DC scaling. So this DC scaling is just to make sure that the gain is 1 when the frequency is 0. And so then here you see I have a bunch of convolutions. I perform multiple convolutions with each other to multiply the filter by itself to get the higher order filters. Then I perform some scaling, and then I generate the feed forward and feedback. But these feed forward and feedbacks are only used in the simulation because I'm not done with my filter, because my filter also needs to include the high pass components. So this feed forward and this feedback are used just to simulate the low pass filter to make sure that the low pass filter is working. So we're gonna go. So if we look at, I believe, impulse invariance, low pass filter, yeah. So I use that and I simulate the low pass filter so it looks like this. And then we take the output. The outputs I'm going to use are the numerator and denominator values. So these values, because I haven't not converted quite yet into the coefficients, because I need the high pass components as well. So this is for impulse low pass filter. I guess we could. I can talk about impulse high pass filter. I don't use this, but it's the same. I have this alpha in here, and then these are the coefficients, and I perform the convolution a number of times to multiply the filter by itself to get the higher order filters. But I will not be using this because this does not scale correctly. All right, next we have the bilinear low pass filter right here. So the bilinear low pass filter, we use the bilinear transform. So this is what the bilinear transform looks like if you put this back over here. Okay, so bilinear transform. This is what it looks like. Here we have 1 and 1 with W cutoff frequency, and then you have this 2 over TS plus the W cutoff frequency, W minus 2 over TS. So that's pretty much just the first order. So I only ever hard code the first order because I can quickly generate the higher order filters by multiplying it by itself using the convolution command. Again, I generate the feed forward and feedback coefficients as if this was just a filter by itself, but I output the numerator and denominator because I'm not done generating the numerator and denominator for the overall bandpass filter. So this is the bilinear high pass filter. It's the same. These values came from our derivation. The bilinear, using bilinear transformation, I perform multiple convolutions to get the higher order filters, and then I output it. And so then this bandpass filter is basically just cascading the low pass filter numerator, denominator, high pass numerator, high pass denominator. So it's just doing the convolution again. So it's going to convolve these two to multiply the two numerators together. It's going to convolve to multiply the two denominators together. And then it's going to actually generate feed forward and feedback coefficients. And these feedback and feed forward coefficients we will actually be using in our C codes. So this one actually will output the coefficients instead of just the numerator and denominator. And so then I take these coefficients and I write them into the different projects in Code Composer. So this program will do both the bilinear impulse and the impulse invariance and the bilinear transform. So right now I have it set to be a bandpass filter from 1500 to 3000. So if I just run this, all right. So bilinear transform, this is what we see. The bilinear transform, you notice that this low pass filter or this bandpass filter, the band doesn't actually ever reach completely 0, and that's because when you have the high pass filter and the low pass filter, the total bandwidth is very narrow. So in order to actually reach a gain of 0 or a gain of 0 dB or 1 with the high pass filter, it requires to be well within the pass band. But at the same time, we also have to be well within the pass band of the low pass filter. And since those two filters intersect very narrowly, you're not going to be able to get a gain of 0, because even though we might be in the pass band of the low pass filter, we would still be attenuated by the high pass filter, or we might be in the pass band of the low pass filter, but we might be slightly attenuated by the high pass filter. So we're never going to be able to get exactly a gain of 0 dB or 1. So notice how this side looks all nice, smooth, and linear, but notice how on this side should also be decreasing at the same rate, at the same dB rate as this side, because they have the same order. But notice how it shoots down extremely quickly. This is because of the nonlinearity associated with the bilinear transform. So when you get to work with the frequencies near the Nyquist sampling frequency right here, you notice that we lose the linearity from the z to the s domain, so we get this distortion. So this distortion right here means that this will not match what an actual filter, because an actual filter will attenuate at the same roll-off rate as over here. And since this is going to be a fourth order, it's going to be 80 dB per decade, because it'll be 20 times 80 dB per decade. So if I quickly, let me find my cutoff frequencies. So my cutoff frequency here is 1500. Oh, this could take a while, so just move really quickly over here. So 1500. So if a single order filter would originally have a cutoff frequency of -3 dB, but since I have 4 of these first order filters, I'm expecting -3 times 4 for -12 dB. But I'm actually at -14, almost -15 dB. And that's because we're seeing some attenuation from the other filter, so from the low pass filter, because this is controlled by the high pass filter. So the low pass filter has a cutoff frequency of 3000. So 3000. Notice what's happened here. When we're at 3000, this does not match the expected cutoff frequency. So it's supposed to be about -15 as well, but it's almost double. It's like almost like negative 30 dB. And that's because we're approaching the limit. Because if I set my sampling frequency to 8000, we're approaching the Nyquist frequency of 4000, so we've lost the linearity. So this doesn't actually exactly match the actual filter. But that's okay, because we can still run this filter. It just won't operate exactly as the actual filter. So this is for the bilinear, because the bilinear has this nonlinearity when you approach the Nyquist frequency. So if we go over here, this is the impulse invariance. Notice the impulse invariance, it doesn't have that sharp cutoff when you reach the when you start approaching the Nyquist frequency, because this doesn't have linearity issues. So where's 3000? So 3000, this should be 1500. So this has a cutoff frequency of 1500, which is closer to -12. But notice how this 3000 isn't exactly at where we thought it would be. So this should ideally be at -12. And that's probably because since this is controlled by the low pass filter, this is controlled by the low pass filter. That means my impulse invariance response to my low pass filter is not quite on it. So let me look at my impulse invariance. Yes. Yeah, the high. Nope. Oh, I know. I remember why. So this is the low pass filter. Let me find that figure real quick. Yeah, so notice how the scaling here is not quite right for the low pass filter. And I'm not 100% sure why the scaling is not quite right. It looks like it looks, so if I take 3000, so notice it doesn't look quite right here, which is why it's not looking correct over there. But I'm not 100% sure why this filter does not match the ideal filter, because if I look at my low pass filter, my impulse response low pass filter, I simply have it set up as this with multiple convolutions. But regardless, if I run this filter, it should run almost relatively normal. I think I might have to go back and look at it again, but just for the sake of this demonstration, I might make a separate video with the correction in there. So let's open up the, let's do, well, I guess we can do the impulse response first. It doesn't really matter. So if I go to the DSP configure header, make sure my sample frequency is 8,000. I have the coefficients that I generate. I have the feed forward and the feedback coefficients right here. I have the IIR filter. So the IIR filter design is going to be the same as with the notch filter. You're going to have the buffers. You're going to have the buffers, and you're going to, oh, well, I want to make sure something real quick. So my order looks like I have an 8th order, so a total of 9 coefficients. So I need to make a small change right here. So this means that it needs to be an 8th order. So I can get rid of 2 of these. So it's going to be an 8th order, get rid of 2 of those. And so this is still the same. I'm going to take the buffer. I'm going to form the dot product, and I do implement shift registers instead of circular buffers because I'm not terribly proficient with pointers and with advanced concepts in C. So with this, we can run. All right, that's fine. So if we run this, all right, so if we take the 1,000 hertz signal, let's bring these closer in here. So this is the 1,000 hertz signal. So if you look, this is the impulse response, I believe. So the impulse response, 1,000 hertz signal is going to be attenuated slightly because I made my filter from 1,500 to 3,000. So this is with slight attenuation on the 1,000 hertz signal. So if I go even lower, so let's say I go to the 500 hertz signal, this should be attenuated more. So now the 500 hertz signal is very attenuated. It's hard to hear. This is at max volume. It's very quiet because of the high order filter gives you the sharp roll off rate. So what's in the bandpass filter is going to be this 2,000 hertz signal. So if I put this up, let me stop this one. And I open this one with the 2,000 hertz. Now this one comes out clearly, or at least more clear, because this one's not as attenuated as much because it's in the pass band. So that's going to be this is with the impulse response low pass filter. So the impulse response, like I said, this inconsistency right here is due to the scaling of the low pass filter that I talked about earlier. But for some reason I can't get this to scale correctly, which I'll go into a separate video probably about explaining the solution to that. So next we need to do the RC. So the RC filter, or not the, well, they're both RC filters, but this RC filter is now going to be using the bilinear. Oh, I forgot to mention, or I guess I did mention earlier, but you cannot use the impulse invariance method for high pass filters. So this, the filters for this, the filter design using for the impulse was use the impulse invariance low pass filter, but it used the bilinear response, bilinear transformation high pass filter. So now this project over here is going to use a bilinear transformation for the low pass and for the high pass. So I'm going to open DSP configure header and make sure my sample frequency is 8,000 just like before. This has not changed except that I need to change the order. So let me make sure. So this is, like I said, this is going to be 8th order, or yeah, it's going to be 8th order because you have 4 4th order low pass with 4th order high pass, so 4 plus 4 for a total order of 8. So let me quickly go here and change the order here to the 8th order. That means I can get rid of 2 of these. I can get rid of 2 of these. All right, so this code's still the same. We still perform the dot product with a loop. We still do shifting using the shift register because I'm not 100% confident in myself to develop pointers for dynamic memory allocation. So with this, we can run the Cascade RC bilinear. So this is using bilinear transformation for the low pass and the high pass now. All right. So we should be good to go. So if I take the 1000, this is with the attenuated slightly because like I said earlier, this here is from 1500 to 3000, so 1000 is going to be attenuated. So if I use a 500 hertz signal, it should be even more attenuated. Yeah, now it's really quiet. This is at max volume. You can barely hear it over the sound of my computer's fan. So this is with that attenuated. At 2000 should be in the passband, so this one should come out to be fairly loud. Yeah, it's fairly loud. Still slightly attenuated because, like I said earlier, since our passband is so narrow and the intersection between our low pass and high pass is so small, we will never reach a gain of 0 dB because we need to be well within. We can never be well within the passband of both filters. And so I guess I can run the 3000 signal, but this one should be, yeah, slightly attenuated because we're now reaching the cutoff frequency of the high pass or of the low pass filter on this end. So that's going to be our demonstration for the RC, for the cascaded RC low pass and high pass filters to make band pass filters. The general design is correct, and the implementation is, I'm pretty sure, correct as well. The only thing that might be slightly incorrect is this inconsistency with the scaling in terms of the low pass filter. Because if I look at, I guess I should have looked at the other filters real quick. So no, we're not going to do high pass. We're going to do, so if we look at the cascaded bilinear low pass filter. So this is bilinear low pass filter, which has a cutoff frequency at 3000. And we see that it has a sharp cutoff rate when you approach the Nyquist frequency, because just like before, once you start approaching that, you lose the linearity. And we can also look at the bilinear high pass filter, which looks like, no, not that one. Bilinear high pass, which is the same sort of deal. Roll upwards. So with this, it doesn't look like I see any sort of attenuation because this gain is 0 dB. So it looks like I don't have, I might see some nonlinearity, but there's definitely some, instead I see some sorts of, right down in the lower frequencies. I noticed there's just like this slight chip right here, or a slight bend, and that's because at the lower frequencies it looks like the high pass filter has problems because the gain is so low. This is in dB, so that might just be a precision issue. So this will conclude our discussion on the cascaded low pass and high pass filters. I will probably make a separate video discussing a solution to that problem that we saw earlier.